A farmer discovered his horse was extraordinarily intelligent. You could ask it an arithmetic problem and it would tap out the answer with a hoof. Researchers were fascinated and tested the horse. They discovered that the horse understood algebra, Euclidean geometry, calculus, and even group theory. However, when they gave the horse problems with Cartesian coordinates, it just stood there dumbly, like any horse. This was quite surprising, given how intelligent the horse was otherwise. So they brought in an expert who examined the situation and explained the problem. Of course, the horse cannot understand Cartesian coordinates, you show it. You are putting Descartes before the horse. And there's an old saying, you never put the cart in front of the horse. Anyways, so let's go ahead and get back to our linear regression and our coordinates on the Cartesian plane. We're looking today at S, the standard deviation of the residuals, R squared still, outliers, and a thing called regression to the mean. So first of all, let's give you this scenario. I got it from StatsMedic, a great source. As part of a new transcript at our school, the counselors have decided to include an IQ score in addition to the GPA. Now, 5 students have requested that the counselors update their transcripts for them. Adam, Bernard, Christy, Deja, and Eldon. It's funny how we always pick alphabetical names, but anyways. So their IQ scores are 110, 85, 120, 95, and 105. But they've been all mixed up and the counselors don't know which IQ scores go with which student. The guidance counselors are forced to predict the IQ for each student. Each counselor takes a different approach. So we have the new guy right here, counselor number 1. So he's totally nervous. He's like, I'll just use the average. All right. So when we add all those scores together, we get an average of 103. And he says, okay, all of them have 103. All right. Then we have counselor number 2, the veteran. And she noticed an equation written on the board in the AP statistics room. IQ equals 16 times GPA plus 57.3. She realized that GPA can help her make better predictions. So she looks up the GPA of each student. And so for Adam, who has a 1.8, we put in 1.8 in for the GPA. 16 times 1.8 plus 57.3, and we get 86.1. And then we do the same for the rest of them. 95.7, 103.7, 111.7, and 118.1. Finally, we have counselor number 3 who says, hey, let me just go ask them. And they pull the students out of class and ask their actual IQ scores. Now we're going to compare the predictions. So first of all, how did counselor number 1 do, the new guy who used the average? Well, his predicted IQ for everybody was 103. His error is going to be actual minus predicted. So negative 18, then negative 8, 7, 2, and 17. Now we're going to go ahead and square these errors. 324, 64, 49, 4, and 289. And when we add them up, we get 730. By the way, one good way to remember how to calculate the residual or the error here, actual minus predicted, like AP, as in AP statistics. So the sum of the squared errors for our first guy is 730. Let's see how counselor number 2, it should say 2 there, the veteran, did. So here's we have the GPAs, we don't need those, and we have the actual and predicted. When we subtract actual and minus predicted, here are residuals. And when we square them, this is what we get. So the sum of the squared errors here is less than 90, much lower than 730. So what was the improvement for the sum of squared errors when using the least squares regression line instead of an average? Well, it's 730 minus 89.9. That was an improvement of 640. What was the percentage improvement? Well, we take that 640 over 730, and it's 0.877. Well, let's go ahead and look at these two pieces again. And we're going to actually use the calculator to determine the correlation, R and R squared. Do you notice that there's something matching here? Our R squared is the same as the percentage of improvement for the sum of the squared errors. So basically, R squared, which is the coefficient of determination, is not only the percent of explained variability, it also is the percentage of improvement in the sum of squared residuals when we use a linear regression instead of just using the average y value to predict y. So now let's go ahead and look at standard deviation. So standard deviation is going to be the sum of these squared residuals, and the formula is divided by n minus 2. So if we calculate the standard deviation of the residuals for our table, we're going to get 5.473. Now let's do the average error for the guidance counselor. His average error is 89.89, number 2, so for the expert, not the one who just used the mean, divided by 5, and then we square root. Kind of like when we were doing standard deviation before. And we got 4.24. Oh, why the difference? It's close. Well, we divided by n equals 5 for the average, and the official formula is actually dividing by n minus 2, in this case 3. So how do we interpret S? It is the actual y context is typically about S away from the number predicted by the least squares regression line. So kind of the way we predict on standard deviation, where we say, oh, that's the average distance from a mean to a data point. This is like standard deviation for the residuals. That's the average distance from the predicted y value to a data point. R squared, like we said before, about R squared percent of the variability in whatever we're measuring is accounted for by the least squares regression line. So let's go ahead and remind you of some formulas, and we're going to go ahead and see how this might impact some of our outliers. So you'll see primarily the formula for B right here, that's the slope, because we can say y equals a plus bx. So this is straight from the formula chart you'll be using on the AP test. And then they have this nice formula, y average equals a plus b times x average. This is b equals your correlation times the standard deviation of y's, not the residuals, but just the standard deviation of y's in general, divided by the standard deviation of your x's. Interesting that you can do that. All right, so let's look at this next applet. I've created this little applet to explore the effect of outliers on the regression, the least squares regression line. So I'm going to go ahead and play with these till I get roughly a 0.8 regression line, and I believe I have a point right there. Beautiful. All right, so I'm going to take this middle point, which is probably helping the regression right now, and I'm going to turn it into an outlier. So the first thing I'm going to do is move it to the far right side of the graph. So what do you see happening to the line? Well, the y-intercept increased because it's honestly kind of flattening out my line, and the slope decreased because the line's being flattened out in this case. Now remember, if this was a negative line, the slope would actually increase. So it depends on what you're looking at. So since I had a positive correlation, this flattened my line, and that's the best way to put it. And this dragged the y-intercept closer to the y-average. All right. Now let's say I put this point far out on the left line. Well, it's still flattening out my line so that the slope actually, instead of being, what was it? The slope was roughly 0.34. Now it decreases to 0.09. So the slope's decreasing, and the y-intercept also increased. Why is that? Well, because it's, again, flattening out the line. That's the easiest way for me to explain it. Now, let's say I take this point and I put it back at the average there. And then instead of going left and right, let's go down then up. So we're going to go below the least squares regression line. As you notice, the slope's not really changing here. If anything, it is shifting the line down. So my slope is the same, and my y-intercept is definitely decreasing. All right, as I shift this up above the line, you can see that it's pretty much, let me put it back on the mean so you can see where it was. So there's the original line. As I shift this up, it increases the y-intercept, but the slope is roughly the same. In all cases, when I have an outlier, my correlation decreases because it's not as good a fit. So let's summarize what we just found out through the applet. If we took a point and we moved it to the far right side along the horizontal, then if the slope was positive, it decreased it because it just flattens it. Same thing if the slope is negative, it's actually going to not really decrease it, but increase it. It's still flattened because it's kind of pulling it along the average, all right? The impact on the y-intercept. If the slope is positive, then, and you pull far to the right, then what that's going to do is increase the y-intercept. But if the slope is negative, it already had a high y-intercept above average, and it's going to decrease the y-intercept. The impact on correlation for either circumstance is that it decreases. Now, if we go to the left, we're pretty much going to see the same effects. All right. So if positive slope, you're going to see a decrease on the slope because it's flattening. Negative slope, you see an increase because flattening. Positive slope, it's lifting the line up towards the average, whereas a negative slope, it's lowering the line towards the average because it's flattening it. And that's for the average y for the intercept. And again, impact is decreases. When we went up and down, we didn't see a lot of change for slope, but this one, it didn't matter what the slope was. We found that the line was just shifting. So when we went below the line, our y-intercept, the whole line is pulled down, so that decreases your y-intercept, and it also decreases your correlation. If you went above the line, then your slope was pretty much the same, but it was pulled up, and that increases your y-intercept, and of course your correlation is decreased. So all are out of pattern outliers, causing a decrease in correlation every time we had a decrease. So what did they have in common? When we went horizontally, that tended to flatten the line. When we went vertically, it just shifted the line. So how did the outliers on the horizontal line for the mean of y affect the least squares regression line in L? Tilted the line, really flattening it, and decreased the correlation. On the vertical line, it just shifted it and decreased the correlation. So which outliers had the greatest impact? And we found out that horizontal outliers actually have more leverage since they are to the left and right of the center of x bar or y bar. Now, that said, we're only talking about outliers that go horizontally versus vertically compared to the average. If you have outliers that have extreme values for both x and y, these are influential and can actually increase correlation as it strengthens the pattern, pulling the line through the point. So for these instances where it's extreme on both x and y, look at which way the line is being pulled by that outlier, and then you'll have to figure it out from the drawing. So let's go ahead and look at an example. We're actually going to use some of the formulas to calculate a linear regression line, and we're also going to determine correlation. So researchers at the University of Denver Infant Study Center, they were trying to determine whether babies take longer to learn to crawl in cold months than warmer months, since they are more bundled up and may not be able to move around. And so they graphed the average age in weeks against the mean temperatures when the babies were 6 months old. So what's the correlation? Well, the correlation in this case, it's a negative slope. So you better put a negative there and take the square root of r squared. Make sure you change it to a decimal. And we get negative 0.6997, which is moderate and negative. Then let's go ahead and identify and interpret in context the coefficient of determination, which is r squared. Well, it's 48.96 percent. So 48.96% of the variability in crawling age is accounted for by the least squares regression line. In other words, in that relationship with temperature. So why do you have to be careful when determining correlation from r squared? Remember that r squared is always positive, but r can be positive or negative. So if you're going backwards, you're always starting with a positive. You need to make sure it matches the sign of the slope of the line. So it might be helpful to write down r equals plus or minus square root of r squared, and then that'll remind you to go check the sign of the slope and use whatever that is. Now you probably noticed another value on there that looks a lot like r squared, called r squared adjusted. What the heck is that? Well, it's a special R-squared value for situations where there's more than one explanatory variable. Good news, we don't deal with that. We just do relationship between one variable and another, not multiple variables. They can happen, and I've actually done that with analytical instrumentation in prior careers. But we're keeping it simple. Ignore R-squared adjusted. Don't touch it. Now we're going to go ahead and see how the heck do we use these formulas that are on your math chart. Well, I did give you a list of data. I gave you the mean temperature, which is our mean x, the standard deviation for our x, the mean y value, which is the mean age, as well as its standard deviation. And we already calculated that r is negative 0.6997. So from that, I can actually go to this and calculate the slope. Typically, we do the slope first and then the y-intercept. So putting in r, there's a negative 0.6997. This 1.76 comes from the standard deviation for y. Remember, y is the response variable. That goes on top. And then x goes on bottom. And we get negative 0.0777. Then we can go ahead and determine what a is. So I'm going to take this equation and substitute. So average age equals a minus, there's my new slope, times average temp. So substituting in the averages, and then I solve for a, and I get 35.67 for my y-intercept. So my new equation is predicted age equals my y-intercept minus, because it's a negative r and a negative slope, 0.0777 times temperature. Notice the hat's only on the age, not the temperature. That's because age is the predicted value and temperature is the explanatory variable. So one of the data points was determined to be an outlier. Circle the data point and explain its effect. So it's this one, and we just learned that's kind of close to the average value. And it's vertically down, so it's just really having a shifting. It's pulling the line down, and of course, it does decrease the correlation. So it reduces the y-intercept and the correlation. The slope's probably still roughly the same. Okay, let's identify and interpret in context the estimate of the intercept for the least squares regression line. All right, so if the temperature is 0 degrees, so we're trying to go all the way back, then we would expect babies to start crawling at 35.7 months. Well, I don't know that babies are going to be more bundled up at 0 degrees than they are at 30 degrees. So that's outside of our data range, and we don't know how it behaves. Also, if we go to really high temperatures, there's no reason to believe that suddenly babies in the tropics are walking around or crawling super early compared to babies in, I don't know, Maryland. All right, so be careful when you go outside of the range of data because there's no guarantee that this is going to continue to behave in a linear fashion. It'll probably flatten out. Okay, so let's examine one more topic called regression to the mean. When we find the least squares regression line, we are minimizing only the residuals, all right? So the distance between the y-coordinate and the predicted value from the line. If you switch x and y, then you would want to minimize the differences for the other variable, all right? So you can't just take a regression line that I said and solve it for x and say, oh, there's your new regression line. No. So you actually have to go and recalculate everything, switching things. So the correlation would still be the same, and why is that? Well, if I switch x and y, what does that do in this formula? It just switches these two in the products. But 3 times 4 is the same as 4 times 3. So correlation is not affected when I switch the two variables. So r will stay the same. So what would be the least squares regression line for temperature versus age? Well, I actually went ahead and calculated it. Predicted temperature equals 250.35 minus 6.298 times the age. And I could have gone and recalculated all these values, switching them, and that's basically what I would have done. Does this mean that we can say crawling age determines temperature? No, just because you have babies that start crawling earlier doesn't mean it's going to get hotter. So the age at which babies crawl does not affect temperature. All right, there is an association between the two, but the causation is not crawling age determines temperature. Otherwise, we could have, if you want to keep it cooler, just don't let that baby crawl. That would be kind of weird. Okay, so in this applet, I have several points, A, B, C, D, E, and I have this automatic regression line that's calculated. No matter where I move the points, the line adjusts. And you can also see the correlation, which is negative 0.72. And here we have the formula for slope on your math chart. That's called B instead of M. And there is the standard deviation of Y and the standard deviation of X. So it's automatically calculating those. And you can see here is the mean point. So the mean X value is 3.86, which is right there. And the mean Y value is 2.98. Now, in this formula, what I actually did is I have the point slope form, which you might remember from geometry, but you can work this out with just having the, and determine the equation by just using the formula on your math chart, which I will show you in the notes. But so here we go. The main thing is as we move these, you can see here's the slope for the original line, and this is the slope for how many standard deviations Y is away from the mean compared to X. So if I take this point, C1, it is about, actually, let's take this point B prime. B prime is roughly -1 standard deviations from the mean value of X. So that means we would expect the Y to be about 0.72 standard deviations above the Y mean. All right, you're probably going, wait, but it's below. Well, that's because the line is not a perfect fit. And so you can see here it's actually a little above, and there it's a little below for the actual points. All right. So the actual points can vary a little more like they actually do in the data. But the line itself, what it's going to use to predict the values, it's going to vary like this. So even if I pull a point way away, let's say I put all these points together, all right, and we're going to get a nice correlation. So this one is about 2 standard deviations away from the mean on the X value, and it's about -2 standard deviations from the mean on the Y value. And you can see that the predicted value in this case is going to go to -0.99. In fact, the strongest I can make this is making a correlation of -1. The predicted value for Y will never vary more in standard deviations than the predicted value for X. Even if I change this to a positive slope, and let me do that, I'm going to move all these points down here. So the most positive I can make this slope is 1, right? And so that's the farthest. But a lot of times, most of our lines are going to have a little bit of scatter. They're going to not be perfectly correlated. And you can see that outlier pulling that line. Now, if I pull it in, it stops pulling it so much. There you go. So let's just say that was our line. In this case, you can barely see that. Can I move it? No. Let me bring my slope down a little bit. Okay, so here you can see that the predicted Y value, let's say X is 3 standard deviations from the mean. That means the predicted Y value would be 3 times 0.7 standard deviations from the mean, which would be 2.1 standard deviations from the mean. So the predicted value, not the actual values. And you can tell by the slope of this line, 1 standard deviation above the mean is just 0.72 or 0.7 standard deviations above the Y mean. So what is this called? This is called regression to the mean, that basically predicted values for Y are never going to be super far away from the average compared to actual values for X and actual values for Y. So if we compare the range of z-scores for the X values and the Y values for different values of R, when R is at the most extreme at 1 or -1, well, then the z-scores for predicted values are close to those z-scores for the explanatory values. But when R is closer to 0, that means the z-scores for predicted values have a smaller magnitude, or at a smaller magnitude than the z-scores for the explanatory values. So what does this mean? When the correlation isn't 1 or -1, the predicted value of y is closer to its mean, y bar, than the value of x to its mean. So that means it pulls the y's, predicted values of y's close to the mean. So 2 more cautions. Remember that correlation and least squares regression lines describe only linear relationships. That's kind of good. We don't have to learn any other relationships so much, so to speak. And correlations and least square regression lines are also not resistant to outliers.